So we had left off, I know I have it erased here, I don't have everything we had yesterday, but we were on example 3. We had just finished example 3, and then I believe we wrote down like the Taylor polynomials for e to the x, sine of x, and cosine of x. And again, those ones, if you don't have them memorized, try to start memorizing those. Make sure they're on note cards. That's something you can practice. Again, all those note cards you made, once you get to that test in a few weeks, are going to be very helpful to study for that test. So you've already made them. You won't have to make new note cards for your studying. As we move on here, it says right here, the 4 special Maclaurin series you must know. E to the x, sine x, cosine x. Those are the 3 we talked about yesterday. And this one, 1 over 1 minus x, which it really relates to like the geometric series. So there's similarities with it, because whenever you found what the geometric series converged to, I think it was the first term over 1 minus the ratio. So that's really what this is going to be. What's the first term of your series here that we were using? Well, if you look at like e to the x and cosine to x, first term was 1. So 1 over 1 minus x, and x would be like where that ratio would be. Now, for the Taylor series for this one, 1 over 1 minus x, this is another one you're going to have to memorize. You should have on a note card or something. Do you want note cards for today? Do you want them passed out, or do you just want to write it in your notes today?
I'll take a note card.
Okay. Note card today?
Sure. So this is like, what would you want to
This is like the e to the x, sine of x, cosine of x, is a series that we're doing. This is another one. It's just going to be the 1 over 1 minus x. So the first term is going to be 1. We're going to have plus x. And then we're going to have plus x squared. And plus x to the third. Plus dot dot dot. Plus x to the n. So that is the pattern of this Taylor series for 1 over 1 minus x. So I know it's another one to memorize, but I don't think it's a very difficult pattern to remember. So there's a 1 over 1 minus x, 1 plus x squared plus x cubed. So x to the nth. All right, so as I mentioned there, those 4 should be ones that you memorize. These series under the operations of calculus behave like the functions they represent on their interval of convergence. So what they're referring to there, e to the x, what we were talking about yesterday, this here acts the same as e to the x does. Okay? So then, for a series with a finite interval of convergence, such as the series for 1 over 1 minus x, if you take the derivative or the integral of it, that radius of convergence that we were finding, that actual radius, it does not change, but it may change the endpoint. So where your interval is at may change, but the actual radius that we were finding in those calculations, the radius will stay the same, whether you manipulate the series or not. So once we have these series memorized, we can conveniently manipulate them to suit other similar non-polynomial functions, as we did in previous sections with Taylor polynomials. So there's 5 things listed below. So it says you can manipulate these 3 special series, or any series we are given, to find another series by using the following techniques. And it says, notice that the radius of convergence may change. So number 1, you can substitute in a series for x. So we had some problems we had done in the last section where instead of x, we had like x squared or something like that. We substituted in and changed instead of just having an x. Multiply or divide a series by a constant or a variable, so just multiplying the existing one. Add or subtract 2 series. And again, that's going to be an interesting one as we look at that later on, because if you think about the series, how many terms does a series have? How many terms are we looking at in this section? Caitlin? Infinite. So if we have 2 series adding together, an infinite plus an infinite amount of terms, so we're going to have those 2 series added together. If we differentiate or integrate a series, it may change the interval but not the radius. That's what I had mentioned up above. And recognize the series as a sum of a geometric power series. And we'll cover that in the next section. All right, so a few of these we're going to go over in the next few examples, so you're going to see exactly what they mean by these 5 things. All right, so let's go to, I guess it would be example 4. So for example 4, they give you an f of x. They give you this series right here. They tell you to find f prime of x, and then once you find that, find f prime of 0. And do you recognize this familiar function? So first we'll go through the process of it, and then we'll see if we see anything is familiar with it. So first thing we need to do is find f prime of x. So again, taking the derivative. So we'll just go term by term. First term, if you take the derivative, what do you get? Derivative of 1. 0. So we don't need to write that. Goes away. Derivative of x. 1. Derivative of x squared over 2 factorial. So you bring down the 2, and the 2 and 2 factorial, that's 2 times 1, so you're just left with x. Very good. Derivative of x cubed over 3 factorial. Close. So you power down, you will have an x squared. And then you would have 3 over 3 factorial. So how do the 3 and 3 factorial cancel? You'd have 3 over 3 factorial. What does that reduce to? If you have a 3 on the top and 3 factorial on the bottom. I guess technically the way you said it as a final answer could be correct, but we're looking for as factorials.
I don't know how that's not
Yeah,
now.
so I see where you're going with it now. So you said 2 because of 2 times 1.
Yeah.
So yeah, 2 factorial. We're going to leave it as a factorial. Sorry about that. Okay, and then if we take the derivative of this term out here, what would that look like? Follow your same rules. You're just going to have n's involved. Power down, you have n, x to the n minus 1 over n factorial. Another way to think about that one could be x to the n minus 1 over n minus 1 factorial. That would be the reduced version. So this original one, if you're plugging into your x to the nth over n factorial, what value does that start at? Starts at n equals what? To get 1 first, then x squared. What value do you have to start with? Try plugging in some numbers. What value would n start with? 0 or 1? Again, I'm ignoring the one we just found, just looking at the original, f of x. What value of n would it start at? Alright, let's try it. So if you plug in 1, x to the 1 is just x over 1. So is your first term x? No. You want to try again? You want to try again? 0, yeah. If you plug in 0, that's where that's going to start. Now let's look at our derivative. So what do we notice about the derivative altogether here? Just looking at the pattern. Okay, it looks exactly the same, but we do notice how our n's are. That looks a little different. So the pattern is going to hold the same for this one, but we're going to have to start at a different n value. So this one starts at n equals what? Yeah, this time it's 1. If you plug in 1, you get x to the 0, which is 1. So they represent the same exact thing, you just have a different starting point. The next part said, well, let's find f prime of 0. F prime of 0, so if I plug in 0 to my f prime function, everywhere there's an x, plug in 0, what do I get for f prime of 0? I have 1 plus 0 plus 0 plus 0 plus 0. Yeah, you get 1. Okay, so that's the value of f prime of 0. So we've answered the first part. The last part says, do you recognize this familiar function? So remember, Taylor series and Taylor polynomials, they represent some other function. Looking at the relationship between the f of x and the derivative, we see that they're identical. We just had to start at different n values, but they're representing the same exact thing. So what function can you think of that this would be representing? E to the x. So let's look. If you have f of x equal e to the x, if you take the derivative of e to the x, what do you get? What is the derivative of e to the x? E to the x. Very good. So again, we got the same exact thing. So this is showing, representing, you get the same exact series. So now, if we took the derivative evaluated at 0, what is e to the 0? 1. Uno. So in conclusion, we can see that the polynomial has the same behavior as the function it represents. So polynomials have the same behavior as their function. That wasn't very nice. Any questions? All right. Let's move on to example 5 then. So example 5. They give you an f of x function there, some Taylor series, and they tell you they want you to find big f of x by taking the integral of f of x dx. And then evaluate big f of x at 0. Well, they tell you that's equal to 1, so they're giving you that. So we need to find what big f of x is. And then do we recognize this familiar function? So after we do all the work, kind of like up above, we recognized it was something familiar to us. So after we do the work, we're going to see if we can recognize what this one is. So what they're telling us to do is we're going to take the integral of both of those. We're taking the integral. So taking the integral of this here. When we take the integral of negative x, what are we going to get? Just think about each term individually. Go ahead. Yeah, we will get negative 1/2 x squared, power up, divide by the power. The integral of the next term, it's going to be x to the 4th over what? You can say it two different ways. X to the 4th over what? So quiet in here. What's on the bottom? Okay, 4 factorial. So another way to think about this, I'm going to write it. If I powered up x to the 4th and I divided by my power, I still have the 3 factorial down there. So 4 times 3 factorial, well, that's just 4 factorial.
Um,
Do you see where that came from now?
I'll just take a guess.
So x to the 4th over 4 factorial. The next one, the x to the 5th over 5 factorial, power up. X to the 6th divided by what factorial? Yes, 6 factorial. Plus dot 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 plus. We have the negative 1 to the n plus 1. And then we need to power up, divide by the power with our general term now. So how would that look? If I power that up, what does the x to 2n plus 1 change to? If you think about this one, originally this was x to the 3rd. How did we get x to the 4th? What's the rule? How did you get from x to the 3rd to x to the 4th? Add 1. So we have x to the 2n plus 1. So what's the rule? So if you add 1, what do you get? X to what?
2x plus 2.
2n plus 2. Yeah. X to the 2n plus 2.
I was close.
I know what you meant. If I divide by the power, the new power is 2n plus 2, so I'm dividing by that whole power. So I have 2n plus 2 and 2n plus 1 factorial. So what factorial actually is on the bottom?
2n plus 3 factorial.
2n plus 2 factorial.
You must have heard me wrong, that's what I said.
So over here, if you look at this example that I had, x to the 4th over 4 times 3 factorial. In this example, it has ended up just being 4 factorial. So this one, just 2n plus 2 factorial. Because remember, it's always 1 less when you take factorials. Yes, Caitlin?
So for C of like before, like on the other page.
Okay.
Like I know we got the 2n plus 3. How did we get that on that one? Like,
Because on that one, all the way back on that problem, they were changing 2n plus 1. Remember, whenever you do the ratio test, every n becomes an n plus 1. Every n you change to an n plus 1. So n becomes n plus 1 now, so that's 2 times n and 2 times 1. So you have 2n plus the 3 now. So if I write that out, you actually have 2 times n plus 1 plus 1. That's in parentheses. So you had to factor 2 to the n, 2 to the 1. 2n plus 2 plus 1 is...
okay, that makes sense.
That's where that came from.
So this one...
This is factorials over here.
We're
Yeah.
just doing, we're just doing like the roll.
Better?
Yeah.
Okay. And as I showed in this example here, if you have 4 times 3 factorial, that's the same as 4 factorial. If we had, say for some reason we had a 5 here, if you had 5 times 4 times 3 factorial, that's the same as 5 factorial, because you're just 1 less each time. All right. So you can rewrite that as just 2n plus 2 factorial, or you can leave it like that for now. When you take an integral, what do we always have to do when taking the integral? Plus c. So if you think about the series, all the series we've been dealing with, c is a what? Constant. Some number value. When we're dealing with these series, if we have any number value or constant, where is it normally written? For the series. Taylor series. At the beginning, because we're going in ascending order. Constant, then if we have x squared, x third, we go in ascending order. So the c comes first. So eventually when we rewrite our final answer, because they want us to write f of x, that c value is going to come first. But don't we know what c actually is if it's the first term? Think about the given information. Well, if I plug in f to the 0 term, what does my first term have to equal?
1.
My first term has to equal 1. What did we say the first term has to be whenever we have a Taylor series? The constant. So the c has to be 1 because that's the first term. So 1 is equal to c. So now if we're finding big f of x, the integral of that original one, the first term, which is your constant because we're going in ascending order, we found that was 1. Where does the rest of this come from? What would be the next term? I guess is a better question. What would be the next term after 1? So,
Writing this.
yeah, we're writing out the actual Taylor series now. So we took the integral to find this one. So we found this and just had c. So basically, what we're trying to do is rewrite this, but we found the constant now. So yes, it's just going to be the rest of it.
1 minus like the 1.
Yes, exactly. This is just rewriting your final answer correctly in ascending order.
Does it matter how many terms
Normally, they'll, usually in like open-ended problems, they'll say like 4 non-zero terms. For this, we're showing 3, which is plenty enough for this example. Because you need to show enough that you understand what the pattern is. Now, let's see. Next. So I'm going to write this as x to the 2n plus 2 over 2n plus 2 factorial Alright, so do you recognize a function that this may represent? Something familiar that we may have dealt with? Look at your original one. Look at our new answer. Good. Which, you're saying cosine for what? For the integral one or the original?
The original would be sine, but the integral one is more like cosine.
Okay, so you're really close with your answers. F of x, big F of x, would be cosine of x, but what else? Cosine of x plus be plus 1. And that's because the original f of x looks like sine x, but what's different about it? It looks like sine x, but what is different? It's negative. It's the opposite. So negative sine x. So the original is negative sine x. If you take the integral, you'd get cosine x plus your 1. Again, that constant came from here. That's why the cosine x has plus 1. They told you what the c value is. So when you take the integral, you have your plus c. So f of x is negative sine x. If you take the integral, cosine x plus 1. And that's how f of x would be represented there. So again, we had the original one and we took an integral to find a different representation. right, I think we have time for another one. This one wasn't too bad, so let's look at example 6. It says, find the Maclaurin series for f of x equal to sine of x squared. Find the first 4 non-zero terms and the general term. So here's one that's specifically telling you how many terms to find. So if we're talking Maclaurin, what does that tell you? What's 0? Center. Okay? So if we're talking about sine, and we know the center is 0, don't we have a memorized Maclaurin series or Taylor series for sine of x? Yeah, what would that be? Starts with what? X minus x to what power? Yep, it's an odd function. Again, it says right the first 4 non-zero, then the general term. Again, we have the alternator. That gives us the odd power. And then the 2n plus 1 factorial on the bottom. So now what they want us to actually find is sine of x squared. So they want us to find sine of x squared. So how do you think we find sine of x squared? Oops. Don't overthink it. What do you think we have to do? Since they're asking for sine of x squared and they're not saying the center is anywhere different, we have this memorized at center of 0. So we can still use this one. We just have to change every x to an x squared. Again, that's because the center is the same. We don't have to worry about it. If I have this x squared raised to the 3rd power, that's actually x to the what? X squared to the 3rd is power to a power. What do you do with them? Multiply. So you would get x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Again, your general term, negative 1 to the n. X squared to the 2n plus 1 over 2n plus 1 factorial. Now on this last term, you can also multiply that out if you want to. It'd be x to the 4n plus 2 if you want to do that. But you could also just leave it as x squared to the 2n plus 1. And that's it for that problem. You use sine of x, which you have memorized. And that's what we talked about on the previous couple pages with those 5 things you're able to do. You have those memorized series, so you're able to use your memorized one to make the manipulated one. They just wanted you to change x to x squared. So having one memorized allows you to do many other things with it, as long as you have that original one memorized. So now you have the first 4 non-zero terms and the general form of this sine of x squared. Any questions? All right, we'll stop for there today. You have a few minutes left, but we're not going to move on to the next one.